Okay, hi everyone. So in this video, we'll be solving some problems involving um, the topology for metric spaces. So these are problems involving open sets, closed sets, limit points, and so on. So most of what we'll be looking at today comes from the course note. So it will either be um, maybe there was a proposition or an example that was left as an exercise in the course note, so it didn't have the solution. We could go through some of that. Or it might have been part of a proof that is in the course notes, but that was skipped over in the lecture slides and left for you all to read through. So in that case, I'll go through the proof one. So in this first question, we'll be looking at, well, it's proposition 2.2.35 in the notes. That number might change depending upon if stuff was added or taken out of the notes, but it should be around that. So this one says, okay, let XD be a metric space. We need to show that the interior is an open set. Well, we could say open set in X, but of course it's understood to be, oh sorry, open, yeah, an open set in X. Of course it's understood to be an open set in X. So I need to say what E is. Then for E, which is a subset of X, the interior is an open set in X. So let's try this proof. So to show that the interior or any set is an open set, we need to show that every point is an interior point. What makes this proof, or what might make this proof a bit confusing, is that we want to show, so I'll just scribble it to the side, is that we want to show that every point every point in the set, which is the interior of E, is an interior point of the interior of E. So we want to show that every point, which is an interior point, so every interior point is an interior point of the interior. So that's what might make this proof a little bit confusing. But you just have to keep track of the sets. Okay, so let X be some point in this set. So I will probably say this set to keep from saying the interior of E, because that might just confuse things. So I'll just say let X be a point in this set. Or if you want to, you could relabel this set like B or something and then redo the proof. But then you need to keep in mind that the elements of B are interior points, because we're going to make use of that later on. Okay, so let X be an element of this set. So, well, this set happens to be the interior of E. So that says that X is an interior point of E. And now we're just going to be applying definition. So if it's an interior point of E, then there will exist some radius. Let's say delta, or let's go epsilon. Then there exists some epsilon bigger than 0, such that I could put open ball around X. So open ball centered at X of radius epsilon, such that this open ball is inside of E. So that's the definition of an interior point. And of course, X is in this open ball, because the center of every open ball is always contained in it. Okay, so uh, now we want to show that X is an interior point of this set, which is the interior. So uh, what we have to do is now construct an open ball around X that is in the interior. Actually, I think it might be better if I draw a picture. So let's say this is a set E. So the interior is always a set inside E. In fact, we'll see in the next one is the is the largest open set inside of E. So there's the interior. So X is this point here. X is a point in the interior. So we know that there exists some open ball of radius epsilon around X inside of E. Now, what we need to do is construct um, an open ball around X. So you see what may happen is that this open ball may fall outside of the interior. If this open ball is entirely inside of the interior, then we're good because then we have an open ball around X inside the interior. Um, so what we need to show is that this open ball is, so how I've drawn it here, this open ball is in the interior. So what we need to show is that is the case because we don't know that this open ball might be in there. For example, let me show you what may happen. For example, this open ball, we don't know if it might be something like this, that this open ball is outside the interior. This is not the case. This is what we need to show. So I want to show, so I'll put here, we need to show that this open ball that we have constructed is not only inside of E, but is also inside of this set, which happens to be, again, the interior of E. If you could show that, then X is an interior point of the interior, and therefore the interior is open. Okay, so in order to show this, again now, so what I need to do is take a point in this open ball. So let's take a Y in this open ball. Okay, so I need to show that this Y is now in the interior. So if this Y is in this open ball, so now we need to make use of the fact that every open ball is an open set. So since every open ball, so this one is an open set, Y is, okay, let's not use interior again, now I'm confused. Let's just so since this open ball is an open set, Y is an interior point of it, so that means that there's going to exist some radius. So let's use delta now, bigger than 0, such that I can put another open ball, this time around Y of radius delta, and this open ball is going to be inside of the open set. But the open set itself is another open ball. And of course, Y belongs to this one. Okay. Um, so we know that, okay. And we know from up here, this part, that the epsilon ball is contained in the interior. So we can add that on to this part, right? We know that this one's contained in the interior. So thus, so what have we done? We have constructed an open ball around this point Y that is inside of this set, okay? And Y is in this open ball. So that means Y must belong to this set, which is what we wanted to show. Okay, we wanted to show this. So we took an element in the first set and we've shown that this element is in the second set. So Y is in there. Um, Therefore, this open ball is contained in here. So that right there, that's basically the proof. So that open ball is in the interior. So what have we done? We've taken an arbitrary point, X, in this set, and we have constructed an open ball around it that is in the same set. Okay, so that means that uh, so X is an interior point of this set that just so happens to also be the interior. Therefore, this set is open. Okay, so that's the proof. So the actual proof is nothing too difficult. The only well, it's not very long, I should say. The actual proof is not very long, but you just need to juggle a couple things in your head because the most confusing part of it is that the set you are working with is the interior. So what you are trying to do is show that every point of the interior of E is an interior point of the interior of E. And that right there is a big mouthful. So that's what you have to sort of juggle, but try drawing out some pictures for it. And eventually over time, as you become more comfortable with these concepts, you won't have to juggle it too much. Okay, so that's the um, first question we wanted to look at. So let me write the next question and we'll come back to it. Okay, so for the second question, we want to show that the interior again, so now we're again with the interior, not only is it an open set like what we just showed, but it is the largest open set inside of E. So what does it mean to be the largest open set inside of E? It just means that if G is any other open set and G happens to be inside of E, so if G is any other open set also in E, then G must be inside of the interior. So again, let me see if I could do a little drawing of it. So that's the set E. So the set E, it might have many open sets. Okay, so all of these are open sets. They may overlap. Some of them may not. So all of these are all the open sets inside of G. What the interior is the interior is the largest open set. So the interior contains all of these open sets. Okay, so this one here, this is the interior of E, and these are like your G. Okay? So G, which are the open sets inside of E, and the interior is this big one. Um, so there's a couple different ways we could prove this. One way is to rewrite this in terms of a set equality, and then we show each side is a subset of the other. So this is usually how it's done in like topology. So we'll do it this way. So another way to say that the interior is the largest open set contained in E is to say that the interior is equal to the union of a collection of subsets. So this collection is going to be a collection of sets. Let's use G. Collections of sets G, which of course are subsets of X. And what is the conditions on these subsets? G must belong to E, and G is an open set. Okay. So in other words, we want to show that the interior is equal to the union of all open sets inside of E. So that's actually how one way you could construct the interior. You take all the open sets inside of E and you just union all of those together. So in order to prove this, we need to show so A subset of B and B subset of E. Okay, so in these proofs, one direction is usually the easy one, and the other one is where we have to do a bit of work. So let's prove that I want to label this something so I don't have to keep writing it back. Um, so let me call this entire thing, let me call that, I don't want to use F. F is usually used for closed set. Let me use A. Okay, so we'll call this entire right hand side A. So proof, so I want to show to prove that this one is a subset of A. So that's the first side. Okay, so this side is the easy side. Because what we've just showed is that the interior is an open set. So since the interior is an open set, and of course, the interior of any set is always contained in that set. Well, the interior satisfies all the properties to be in this union. And that means that the interior is one of these sets that we are unioning over. So the interior is in that collection that we are doing the union over. Yeah, so since the interior is an open set and it's contained in E, then of course the interior, so I'll put it like this, the interior belongs to this collection. Okay, so the interior belongs to this collection. So of course, then the interior is a subset of the union of this collection that I'm calling E. Okay, so one side we've done. So the other side, okay, so now for the converse part. So now we're required to prove that A is a subset of the interior. Okay, so what I'm going to do is let me take a point in A and we'll see if we could show that that is in the interior. So let X be some element in A. So now remember A is the union over this collection. So A is the union over a whole collections of open sets. So if X belongs to the union of all these collections of open sets, then X must be in at least one of them. So then X belongs to, let's say, G. So X is one of them. So let's just say X belongs to G for some G in that collection. For some, let me say, for some open set G in E. Okay, that's just another way of saying X is one of the sets in this collection. Okay, because what are the sets in that collection? Well, those are open sets contained in E. So X is in one of them. Let's call it G. So G is an open set. So then X is an interior point of G. Then X is an interior point of the set G because G is open. So of course, what does that mean? That means that there exists some radius such that I could put an open ball around X of that radius, and this open ball is going to be inside of G. Now, all we need to now see is that, okay, obviously this G is going to be contained in the union over all of them. Okay, over the union over all of them is what I was calling E. So G is one of the set in that union. So G is obviously contained in the union, which I'm calling E. Okay, so then what do we have? Well, now we have shown that if I take any point in A, I could find some radius such that I could put a neighborhood around that point, or I shouldn't say neighborhood, an open ball around that point entirely contained in E. So therefore, X is an open set of E. Actually, actually, we don't need we don't need A here. We need E, right? Because if I want to show X is in the interior of E, I need to show X is an interior point of E, right? So it wasn't A we need. Sorry about that. It was E because G is in E, right? G is a subset of E. So it's even easier. G is in E. So thus X is an interior point of E, which means X is in the interior. So we've shown that A is a subset of the interior. So therefore, the interior is equal to A, right? And that's your proof there. Okay, so in this next example, we're going to look at the proof of this theorem 2.4.6. So the proof of this one is in the course notes, but I'll just discuss it with you since it wasn't proved in class. So this one is saying that if P is a limit point of the set E, then every open ball contains infinitely many points of E. Okay, so actually this is one of the ways you should start thinking about what a limit point of a set is. So I'll just do a little picture. So if this is your set E, and now the limit point does not have to be in E, but I'll just draw it in E. Because the limit point might be outside of E. So if P is a limit point of E, then what this is saying is that if you put any open ball around it, right, no matter how big or how small, there are always going to be infinitely many points of E inside of this. So no matter how small you then shrink this open ball around the point P, you will always find infinitely many points of E around it. And we'll talk about after a very useful corollary that comes out of that, which is that if you have a finite set, then that finite set has no limit points. Because, well, if it did have a limit point, then I could put an open ball around it, but that open ball then should have infinitely many points of that finite set. So how can I have infinitely many points of a finite set? So right away, it tells you that, okay, if you're looking at a finite set, there are no limit points there. The derived set of it is empty. Okay, so how to prove this? So it's a proof by contradiction. Um, so what we're going to do is suppose P is a limit point of E. So suppose P is a limit point, and I'll write LP for limit point of the set E, and I'm going to assume the negation of what I want to prove. and assume that um, there's an open ball. So assume that there exists, so there, okay, exists an open ball. So open ball centered at P of some radius, epsilon, um, containing, so the negation would be that this open ball contains finitely many points. So containing finitely points of E. So I want to see if I could get a contradiction from this. Okay, so if it has finitely many points of E, let me label those points. So let's say, so call these points, so the nodes they use, I think Q, so let's stick to that. Q1, Q2, Q3, so let's say you have N of them, Qn. Okay, and all these points are different from the point P, um, which are all different from the point P. So you're not allowed to choose P as one of these points. So what we're going to do now, the only thing you really need to remember in this proof is that once you have these points, you just need to choose your epsilon as the minimum distance between all of them. So let me give you the picture of what's going on. So this is your set E. So again, I'll put the limit point inside E, but again, it doesn't have to be inside of E. So that's the limit point P. This is your one ball. So that's your so that's your open ball. And inside of this has finitely many points of E. So these are the Qs. So here's, let's say this is Q1, Q2, Q3, and so on, right? So these are the finitely many points of E. Let me use a different color for those points, so we won't confuse it with the open ball. So these are the points. So Q1, Q2, Q3, Q4, Q5, let's say. So the idea is you're just going to now measure the distance between P and all of these points. So, so you want to measure the distance between all of them, right? Measure the distance between all of them. Okay. Right? And then you take the minimum of those distance and that you choose as an epsilon. So you could say let epsilon equal to the minimum over the set of all distances from P to these Q. So let's go Qi, where I ranges from 1 to n. Okay, so epsilon will be the minimum of those distances. So now, if you look at the picture, now if I then construct around P another open ball of radius, let's say less than this epsilon. So if I now construct an open ball like this, with radius less than that epsilon, then there will be none of these red points in that ball. So In other words, I can now construct an open ball around P that has none of these Q's inside of it. And that's going to be a problem because we assume P is a limit point. So, um, uh, so we could just say that this implies that the open ball centered at P of radius. Oh no, I used epsilon before. I use epsilon over here. So let me change this one to delta, right? So we don't get confused. So I'll try to picture. So this first open ball is radius delta, right? That one is delta. Yeah. Did I use epsilon again? No. Yeah, so the big ball is delta, and now I use an epsilon inside. So then I guess the cosinus would have used R or something. Anyway, so the open ball centered at P of radius epsilon cannot or does not contain any of these points, any QIs. So what have we found? We have found an open ball around P that does not contain any point of E. That is the negation of the definition of a limit point. So also we could write that as, so then this ball radius epsilon center P intersection E will only have one point of E. Of course, that's the center P, because we assume P was a point of E. Actually, yeah, okay, it's P. So this means that P cannot be a limit point of E. Remember, for limit points, you're not allowed to choose the same point to be so a limit point means that if you have some set, a limit point means that if you take any open ball, no matter how big or how small, around that point, you will always find another point of the set in there. That point of the set, you are not allowed to choose as the center. So you need to choose a different point. Okay, so we can't choose. So if P happen to be an element of E, which in this case, how I drew it is, you still can't choose that to be your point. You can't say, oh, well, if you put a ball around P, there will always be a point of E. That's the center P. You have to find a different point. You cannot you cannot take the center. Okay, so P cannot be a limit point of E, but what did we assume in our first line? We say, suppose that P is a limit point of E. Okay, so that's your contradiction, which is a contradiction. Which is a contradiction, right? So therefore, you have to prove. So every open ball around a limit point will have infinitely many points of that set. Okay, so for our next question, we'll look at what's in the course note right now listed as term 2.4.23. So this one has to do with some properties of the closure of a set. So just to recall, that the closure of some set is just a set together with all of its limit points. And the set of limit points, you write it as E prime, and the fancy name for it is the derived set. So the closure is the set union its derived set. There are other definitions of how to construct the closure. So if you like look at a topology book, they might have the closure defined differently, but all of those different definitions, they are all equivalent, they all imply each other. So it doesn't matter which one you choose as your definition, because you could always prove that it is equivalent to all the others. Um, so just something to be aware of. Okay, so we want to show that the closure is a closed set, or it's closed in X. So just like the interior was an open set, the closure is a closed set. Okay, so the proof of this. So to prove this, there are a few ways you could do it. So we'll stick to what is done in the notes, which is to show that the um, closure, the complement of it is an open set. So I'll put you're required to prove because the set is closed if and only if the complement is open. So I want to show that the complement of this is an open set. Okay, so if I can show that the complement of it is an open set, then the set will be closed. So now again, it goes back to how do you show a set is open? Well, you need to show every point is an interior point. So let's take a point of the complement. So let P be a point of the complement of the closure. Then now remember that the closure is the set union. It's a limit point. So the complement, so if you have a point in the complement of that, then that point cannot be in E. That point cannot be in E, and it cannot be in E prime. So then P, of course, is not in E, and also P is not in E prime. Otherwise, it would have been in the closure. So P is not a point of E and is not in E prime. So if P is not in E prime, then it's not a limit point of E. So this implies that P is not a limit point of the set E. Okay, so P is not a limit point of the set E. So if you're not a limit point, we need to go back to what is the negation of being a limit point. If you are not a limit point, so to draw a picture, E, so here's P. If you are not a limit point, then that means you could find an open ball around that point that has no points of E inside of it. And of course, when I say no points of E inside of it, I am not counting the center. I'm not counting P. But in this case, P would not even count because look, P is not an element of E. So P will not even count. So you can sort of see that this open ball is in E complement. Okay, because if E is the set, out here is E complement. Okay, but we'll get to that. So P, this implies P is not the limit point of E, hence there exists some radius bigger than 0 such that if I put an open ball of that radius around P and I intersect it, so it has no points of E. So if I intersect it with E, it should be empty because there should be no points of E inside of it. Not even the center, because the center P, I assume, was not an E. Okay, so this is a result that you may have seen it. Well, hopefully you will have seen it in undergrad. A intersection B equals to empty set if and only if A is contained in B complement. Right? So that's another result that you might need. So I'm just going to apply that result here. Okay. So if two sets are disjoint, then that means they belong to the complement of the other. So from here, that means that this open ball must belong to E complement. Uh, yeah, so this open ball must belong to E complement. Um, so I want to show, what do I want to show? I want to show that E bar complement is an open set. So I want to construct an open ball around P inside of E bar complement. But I have constructed an open ball around P inside of E complement. Oh, okay. So um, a E bar complement. So E complement is of course in E bar complement. Okay. Um, that's because okay. So let me rewind this a bit, and I can explain to you why it's an E bar complement. It has to do with the definition up here. But instead of E, like you're replacing it with E bar complement. Um, but there's an easier way we could do this. So um, since so the open ball intersection E is empty. So therefore, if I intersect this open ball with with E bar, that will also be empty. Um, so since I could just say implies. So this then implies that the open ball, if it intersects E and it's empty, then when we intersect it with E bar, it will also be empty. Okay, so now it's a bit clear to see. So that means that this open ball must be entirely contained inside the complement of E bar, which is what I want. So what have we done? We've taken a point P in some set, and we have constructed an open ball around that point entirely within that set. So thus P is an interior point of that set, which happens to be E bar complement. But P was an arbitrary point, so every point of this set is open. So therefore, E bar complement, every point of E bar complement is an interior point. So E bar complement is an open set, which means, so there's a if and when here, which means that E bar is closed, which is what we wanted. And so not only is E bar closed, okay, so let's say this is E. We know that the interior, so this is how the story goes. The relationship between the interior and the closure. The interior of a set is the largest open set inside of it. Okay, so the interior of a set is the largest open set inside of it. The closure now, actually, let me do this. Okay, so this is E. I see. So the closure now is the smallest closed set that contains it, or that contains E. Okay? So this guy out here, that's the closure. So the closure, the interior is the largest open set inside E, and the closure is the smallest closed set that contains E. Okay, so if you have another closed set, so let's say um, uh, F, F is a closed set and E is inside of F, then the closure is also inside of F. So any closed set that has E also has its closure, right? And there's a proof for that. You should try to prove it. It's done in a similar way to the interior proof, except in that one, you're going to intersect all closed sets containing E. So you collect together all the closed sets that contain E and you intersect all of those together, and that's what this thing is. Okay, so the next part in the same theorem that we want to prove is that if E or E is equal to its closure, or any set is equal to its closure, if and only if that set is closed. So it's an if and only if statement, so we need to prove two directions. So let's try this direction first. So suppose that E is equal to its closure. Now we just saw in the part before that the closure is a closed set. So therefore E is closed. So suppose E is equal to its closure. Since the closure is a closed set, E is closed. Right? So that part very easy. The next part is also easy. So next side, suppose E is closed. Okay, we want to show that it is equal to its closure. So, so if E is closed, then it contains all its limit points. So a set is closed if and only if it contains all its limit points. So if E is closed, it contains all its limit points. Limit points. That means that the derived set, the set of all limit points, is a subset of E because it contains all its limit points. And the closure now, the formula for the closure is E union the derived set. So if you take any set now, let's say here's A and here's B. Of course, the union of these two sets is the bigger set, right? If B is a subset of A, then the union is A. So it's the same thing here. E prime is a subset of E, therefore the union of them is the bigger set, which is E. And that's what we want to prove. And that's to prove this one, very easy. Okay, so in part C of the same theorem, we need to prove something that I said after the proof of the first part, which was that the closure is the smallest closed set contained in E. So this is another way of saying that. Well, this is the technical way of saying that. So it says that if the closure is contained in some set F, where F is a closed set, oh sorry, I said it wrong. It says that the closure is contained in F for every closed set F such that E is contained in F. Okay, so again, the picture for this is that so if here is E, and if you have some closed set F, so if you have some closed set F closed, so if F is some closed set containing E, then F will also contain the closure. Okay, so the closure is the smallest closure from there. So this one here is the closure. Okay, so if you have a closed set that has the closure is also in F. Okay, so how to prove this one? Prove. So suppose F is closed. So suppose F is a closed set and E is contained in F, or F contains E. Ah, okay, so what does it mean to be closed? So since F is closed, that means it contains all its limit points, or the derived set is contained in it. And the derived set is contained in F. But what do I know? I know E is also contained in F. But E is also contained in F. And what I could do, so we will need to prove this though. Because I don't think we did the proof of this in class either. Anyway, we could prove it afterwards. So basically, if you have a subset relation, you are allowed to take derived sets on both sides. It actually is the same thing for interior. So we could prove these things. So if A is subset of B, then the interior of A is contained in the interior of B. The derived set of A is contained in the derived set of B, and the closure of A is contained in the closure of B. Right? But you will have to prove those things. So we're using the one with the derived set. Okay, so if E is subset of F, then the derived set of E is contained in the derived set of F. And from right above here, the derived set of F is contained in F. So I'm just going to add on that part. Okay, so this implies that the derived set of E is contained in F. Okay, yeah. So so I have two things. So E is contained in F, and the derived set of E is also contained in F. Therefore, the union, so union both sides. So E union E prime is also contained in F, but what is E union E prime? That is just E bar. Okay, which is what we want to show. Okay, well, let's quickly prove that result we use, that E prime, that you are allowed to take derived sets. Uh, the proof for this, I don't think it's long. We'll see. So let's prove this one. So if A is a subset of B, then A prime subset of B prime. Okay, the proof of this is suppose A subset of B, suppose A subset of B, so I want to show A prime is subset of B prime, so I take an element in A prime, and let X be some element in A prime. I want to show X is in B prime. Then X is a limit point of A. Okay, so What does that mean? So straight definition of limit point, it means for any epsilon bigger than 0, the open ball of radius epsilon centered at x intersect or it contains at least one point of A different from the center. So you could say intersect A is non-empty. Right? Technically, this should be a deleted ball, but I don't think you all did deleted ball. Deleted ball or deleted spheres or deleted neighborhoods. It's usually written like this with a little star above. This is just the open ball, the usual open ball, but you remove the center. So minus the center. So it's the entire open ball, but you take out the center from the set. So technically it should be this. Because what can happen, X could be an element of A. Therefore, this open ball intersect A would equal to X. Okay, so we could do that. So let's use the deleted one more. Deleted open ball. Okay. So that's the one you need to use for the limit point. So the deleted open ball, center at x, radius epsilon, intersect A is non-empty. But A is a subset of B. Therefore, so I'll direct this. And since let's see this A subset of B, so I'm going to intersect both sides with the open ball. So let's do it like this. Open ball, radius epsilon, centered x, deleted because I want to remove the neighborhood. Oh, sorry, the center. Intersection A, right? Contains. So I intersecting both sides with this set. Intersection B. And I know this guy here is non-empty. Okay, so you have a non-empty set contained inside of this set. So this implies that there exists some y inside of this set. And I was saying I shouldn't have used B either. Because B for open ball, B for set B. Anyway, I'll have to get used to the same letters written around. So there exists some y in this intersection. And since this works for any epsilon, then that means, I'll write it like this. This implies that for any epsilon bigger than 0, this set is non-empty. Therefore, x is a limit point of B, right? So that's what we wanted to show. We took an element in A prime and we showed that it belonged to B prime. So we write it like, so x belongs to B prime. Yeah, so that's a proof of that one.